let's talk about the lungs. So this represents a lung, one of your two lungs. You do have two, in case you were wondering. We've got two lungs, and this has composed of two membranes, three spaces. So this outside layer, we call it the visceral layer. This is the part that you usually see because it's on the outside. And then we have this inside part, we call it the parietal layer. That was awful, but you get the idea. But what they do is they compose another space in here that's called the parietal, or pleural space. And this facilitates something called the interpleural pressure. This has a -5 millimeters mercury to it. And that fluctuates between -5 and -1 depending on whether your lungs are inflated or deflated. But point being is air comes, or as we breathe out, this pressure is going to decrease, and as we breathe in, it's going to increase. I guess I got that backwards. Become more negative as we breathe out and more positive as we breathe in. Because that allows the lungs to contract. Anyways, cool. So that's fun. This is a bronchi, but really it's an alveoli. Bronchi, alveoli. Cool. So there's this problem we have with air, or problem we have with these balloon-like things. We have a small one and a large one, and it's kind of like a balloon. This is really counterintuitive, because when air comes in, we would think, oh, they're going to fill up evenly, but wrong. This part's a lot harder to fill up than this part, and that comes from Laplace's law. So pressure is equal to 2 times the tension divided by the radius. So if we have a small radius, like we do with the small guy here, that's going to equal a big pressure because it's on the bottom, so it's inversely correlated. And if we have a large tension, again, it's going to equal big pressure. Well, it turns out in the small one, because its fibers are closer together, it's a lot harder to make it blow up, so therefore it has a high tension, which creates a really high pressure. So if we were just to let these two do their thing, only this one is going to inflate, and this one's just going to stay how it is, because it's happy to do so. This is an area of low pressure, this is an area of high pressure, so the air wants to flow over there. Oh no, how do we fix this so we can breathe? Let me tell you, we use, or God uses, something called surfactant. Surfactant is a chemical that our body produces that decreases the surface tension of water. So the reason why this wants to like that is because water wants to attract to itself, but if we decrease the surface tension, we are decreasing tension. Can't do anything about the radius. Well, we can when we breathe, but that's what we're trying to do. Can't do anything about the tension, or I just said that. No, can't do anything about the radius, but we can do something about the tension with the surfactant. So here we still have some surfactant on the large one, but on the small one we have a ton of surfactant, disproportional amount. That decreases the tension, so the two pressures are more or less equal, and we get even inflation and deflation. Cool. Now we have O2. We have O2 here. That's fun. And O2 is able to fly out like that due to the 102 millimeters mercury that exists in here for O2 and a smaller amount here. And we have about 40 millimeters of CO2, about 45 millimeters of mercury pressure here inside the bloodline, and we only have about 40 here. So CO2 wants to come off, O2 wants to go in. I mean, if it didn't, we wouldn't breathe, so there's that. And that's gonna go and go and go until we hit right here, in which case the O2 now has a higher pressure here and a lower pressure inside the cell. So O2 is going to fly off and CO2 is going to fly on to our deal. But CO2 doesn't like to stay in that form, so carbonic anhydrase comes and does a conversion, converts it to bicarbonate and a hydrogen ion. Bicarbonate is going to leave because it can. Hydrogen is going to stay, but we have to replace the negative charge, so we do the chloride shift. Chloride shift comes in to stabilize our charge. That's going to go on through until we get to back near the lungs, in which case we're going to undo the chloride shift. Bicarbonate is going to come back in. Carbonic anhydrase is going to convert back to CO2 and rinse and repeat. That's how we breathe. there is another factor to this called the oxygen saturation curve. So I'll draw you a normal one first so you know what we're looking at. Whoa, that was weird. It's supposed to be sigmoidal like that. Anyways, so what this represents is that for how much pressure of oxygen here do we get a percent saturation here. So if this is 100%, let's say that's, I don't know, 100 millimeters mercury or something like that. About right here, let's call it 75%-ish, and 40 millimeters of oxygen, we're going to have 100% saturation. But this curve can be shifted depending on some factors. So factors include our concentration of CO2 in the blood. We have a concentration of our hydrogen ions in the blood. We have the presence of a glycolysis byproduct called 2,3-BPG, which is biphosphoglycerate. And we also have temperature as a factor. C, D, I think that's everything. I think I'm missing anything. Yeah. So these things cause hemoglobin to not bind as tightly to oxygen, and that's what we call a right shift curve. So if I were to draw that, still starting from here, and then it gets up to 100%. I just didn't draw it right. It just takes more oxygen to get the same degree of saturation. But if we decrease these factors, then we get what they call a left shift curve. And it requires less oxygen to get the same factor. Just a little quip. Carbon monoxide has a 400 times binding affinity more than oxygen to hemoglobin, but it's going to look like a left shift curve because it forces hemoglobin into the R state. The R state is what we're actually kind of measuring when we look up percent saturation, which is important. So yeah, don't get that wrong. Boom! You just got a pneumothorax. Forgot to talk about that. So pneumothorax is when we have a puncture this way, or a puncture this way, or heck, all the way through. If you really want to be kind of stabbed, it means you got stabbed. You did get stabbed. I just stabbed you. That's going to allow air into the interpleural space, which gets rid of that -5 millimeters of mercury pressure, and our lungs can go whoop. It's going to collapse because it can. These muscles are going to be able to overdo what they were trying to do.